each of you to this webinar. Let me start by saying, perhaps there is no greater act of human kindness than to simply offer a thirsty person a drink of water. It is in that grace I wish to thank you for the important work that you do to provide clean drinking water for your communities, and then for your time to allow us to share our knowledge regarding water disinfection technologies, and in particular, maintaining safe drinking water in long-term storage applications. For today, the flow of our discussion will include a baseline metric to understand the demand for clean water, followed by a presentation of the results from a survey that many of you completed prior to this webinar. This discussion will lead us into a guideline that we created following a discussion with a UN panel, followed by a comparison of methods commonly used for treatment and storage. Oops. We will conclude today's webinar with a discussion of 2 alternative solutions to treat and maintain safe drinking water in long-term storage applications. We have a full agenda, so I will allow Q&A at certain times. If you have questions, then please use the chat box at the bottom of the screen, and we will do our best to answer them here or in an email later. Finally, should you be interested in these 2 alternative solutions, we will provide some information regarding a trial to support your mission at home. Okay, let's start with a basic metric to understand the demand for clean water. According to a 2002 UN report, the minimum amount of water a person needs each day is about 13 gallons or 50 liters. Of those 50 liters, 20 are for sanitation and hygiene, 15 for bathing, 10 for prepared food, and 5 for drinking. When you take this estimate and multiply it by the population in each of your home countries, that is a large volume of water, and equally a large responsibility to ensure the water is treated and maintained in storage properly. And that estimate does not include volume required for commercial uses, such as in hotels, hospitals, schools, or businesses. There are several technologies to initially clean water for drinking. Filtration, probably the oldest method used, boiling, another early method, and several technologies that are equipment intensive, as well as technologies that introduce chemicals as disinfectant. From a survey conducted among 31 CAWASA members, all of them mentioned chlorination as a method used to initially clean water. There are a few other methods also reported. When asked about methods to keep water clean in storage, CAWASA members mentioned a variety of methods, including monitoring of chlorine residual, post-chlorination when needed, and providing a fully covered tank to prevent contamination from animal droppings, debris, or other waste products. There are several water quality problems that are often experienced with long-term storage. Contaminants from chemicals or from storage tank corrosion, contaminants from disinfection byproducts, growth of biofilm or algae, and reemergence of waterborne bacteria, which is created in part by the decay of disinfection effectiveness. There are several other issues that impact water quality, and some of these can also affect taste and odors at the point of consumption. When asked about water quality problems typically experienced, CAWASA members cite all of these issues, most notably sediment, corrosion of storage tanks, and taste and odors. Note that tastes and odors can also be created from the presence of disinfection byproducts and biofilm or algae. Of the water quality problems cited by CAWASA members, there are several problems highlighted here that represent health risks to your communities. Hence, you are faced with a challenge of meeting water demand and minimizing the health risks associated with cleaning and maintaining safe water and storage. In light of this challenge, let's visit the question, what makes a water disinfectant effective? During a discussion with the United Nations panel, we created a guideline from their input on what the term effective truly means. The disinfectant must be lethal and appropriate for the particular need. It must be safe to use, easy to use, and, if necessary, portable to use. It must have a neutral taste or odor. It must be compatible with the storage container. And it must be friendly to the environment and have a long shelf life. Given that all surveyed CAWASA members cited chlorination for treatment, of these factors shown here, presence of health side effects and bad taste and odors are two factors that are commonly associated with this method of treatment. And from the survey, formation of harmful byproducts associated with chlorine disinfection is one of the water quality problems that you typically experience with storage. Chlorine and disinfection byproducts linked to chlorination often lead to taste and odor issues. In fact, there are many compounds that are produced as a result of chlorination. Of the compounds listed here, there are several compounds called trihalomethanes, which have been linked to cancer and other health risks. We acknowledge that for nearly 50 years, chlorine-based solutions have been widely accepted as a solution for point-of-use applications in the form of chlorine tablets and as a solution for large volume applications in the form of tablets and liquid. And the overwhelming vast majority of users, well, they are using that project very safely. However, the opportunity exists where over-coordination is possible, leading to significant health risks. These risks include cancer and issues related to women's reproductive and children's health. As mentioned earlier, disinfection by chlorine produces trihalomethanes. And there have been many published studies linking these disinfection byproducts to health issues. For example, in a 2007 study conducted in Taiwan, researchers observed a significant increase in a few birth defects. These findings, as well as those in other research studies, require an emphasis on monitoring chlorine residual as utilities are faced with the challenge of meeting water demand and minimizing the health risks associated with cleaning and maintaining safe water and storage. The disinfection of water for human consumption, of undoubted importance to human health, can be accomplished through a variety of methods and technologies. In this chart, we see chlorine-based solutions as highly effective in killing waterborne bacteria and some viruses. And even with some of the limitations reported here, chlorination is perhaps the most widely used solution in developed countries and major cities in developing countries. Though commonly used, this method has struggled in many rural areas due to cultural, logistical, and technical hurdles. While reasonably priced, chlorination suffers from issues including transportation and storage of its concentrated form, dangers and risks from its handling and dispensing, and the technical skill to use monitoring equipment and to properly redose the water supply. The opportunity to bring simple, low-cost, easy-to-operate solutions to initially clean water and keep water clean during long-term storage will benefit rural and urban communities alike. One such solution is the use of mixed oxidant gases. Not only do mixed oxidant gases kill all waterborne bacteria, but they also eliminate viruses, protozoa, parasites. And because far less chlorine is required in the disinfection process, there is a significant reduction in harmful disinfection byproducts. And you will also notice exceptionally good tasting water without the unpleasant taste or odor often found in typical chlorinated water. I submit to you here that as part of the solution to meet the water demand and minimize the health risks associated with cleaning and maintaining safe water and storage, mixed oxidant gas disinfection should be highly considered by each member of CAWASA. I'll take some questions in a few minutes, but first I'd like to describe this technology to the group here today. For reference, I'll refer to the oxidant gas regeneration equipment as OGRE. By controlled electrolytic decomposition of common salt, OGRE generates a mix of highly volatile oxidant gases, which completely eliminates bacteria, viruses, protozoa, and parasites. And it does so at a very low cost, safely, and when minimal maintenance required. This unit here can disinfect up to 1 million liters of contaminated water per day. I already mentioned the effectiveness of OGRE as a water disinfectant. Disinfection occurs when these mixed oxidant gases, which have a very short half-life, are dispersed into a stream of water, for example, through a pipe. The proprietary mix of these gases from the unit that we initially developed for a United Nations project makes OGRE unique in its technology, its application, and far advanced in how we envision disinfection to be for either initially cleaning water or keeping water clean in long-term storage. Here are just some of the gases generated in OGRE. Note that with the presence of this mix of gases, most of the burden to disinfect the water is placed on gases other than chlorine, thereby greatly reducing the amount of harmful byproducts associated with chlorination. The resulting potable water has a very pleasant taste and virtually no odor. Only 1 part per million of residual chlorine is created by this process. Operationally, the only consumable material in OGRE is table salt. Electrical power can be generated by an AC or DC power source, even a car battery or small solar panel that supplies the current necessary to operate this unit. The generation of oxidant gases is controlled by a potentiometer and is measured with an ammeter and voltmeter incorporated into the source. The oxidant gases generated are brought into the water distribution system through a Venturi injector, which absorbs the gases from the OGRE and disperses them into the water flow. In a few minutes, I'll show you various illustrations in which an OGRE can be incorporated into a system for initially cleaning and keeping water clean in storage. But a couple of comments on maintenance. The only material that needs to be replaced on a periodic basis is table salt. And because OGRE can be set up to recirculate water held in long-term storage, there is no need to test the cleanliness of the water or dose the storage container with any chemicals. Rather, to ensure the water in storage stays safe, simply turn on the unit and allow the stored water to run through the Venturi injector again. That's all there is to it. A few moments ago, I mentioned that we developed the OGRE unit for a United Nations project whose purpose was to design and implement a technology that could both initially clean water and keep it clean in long-term storage. Essentially, a community water point was designed and built to incorporate an Ogre unit, shown here. Water is pumped from a water source, typically a borehole, through the Venturi injector and into a storage tank. Families access the clean water from the outside faucets. About 25 of these community water points were built in various rural parts of Mexico, and they all operated as intended. Once the project was completed, operation and maintenance were turned over to the local community members. Here is another location where the Ogre unit sits on a table adjacent to a storage tank. The UN project was a great success, as these community water points were available to provide families easy access to safe water on a continuous basis, all in areas with no or limited access to municipal water distribution. In a minute or so, I will open up our webinar for Q&A, but first I would like to highlight how Ogre can operate to initially treat and keep water clean in storage in several configurations. In this configuration, incoming contaminated water can be cleaned as it goes through the Venturi injector and then deposited into a storage tank. Ogre can also be configured to operate in line with a water distribution pipeline. And here, Ogre can be configured to keep water clean for long-term storage. A recirculation pump is required to turn over the volume of water stored to ensure the water stays safe on a continuous basis. At this point, let me pause and see if you have any questions about Ogre or other information that we have discussed. And Bill, if there's been any questions in chat box, please address those or perhaps any that were sent from the survey. Bill, I think you're on mute.
There are no questions in the chat box, David.
Okay. What about any of the questions that were raised during the survey that we had sent out last week, particularly about how long should the chlorine stay in a storage tank and what residual might be required to ensure that water does stay safe for a long period of time?
In general terms, and Don Jose may be able to help me on this, but in general terms, 1 to 2 parts per million of chlorine is enough to sustain the water in a safe condition. Unfortunately, if that is vented, open to sunlight, or open to any kind of contamination whatsoever, you're looking at something probably in the 72-hour range. And if you are strictly chlorine disinfected, you really want to make sure you're taking a look at that water every 72 hours and adjusting the chlorine level.
Okay, great. So for the members that are attending this webinar, please feel free to add questions to the chat box, and we'll try to address them at another point here during the presentation, or you can certainly email me with those questions. But for now, let me go ahead and continue on with the presentation. So for the remaining time that we have today, I would like to discuss an alternative to chlorine-based solutions. One alternative that has piqued the interest of water sector professionals who are looking to avoid the health risks associated with byproducts from chlorination is a solution that is silver-based. Silver-based disinfection products have a considerable long history of antimicrobial performance. Ancient Greeks and Romans used silver to disinfect water and food supplies. Ancient Egyptians used silver to treat burns and wounds. As late as World War II, silver salts were used as antibiotics to treat wounds on the battlefield, Today, silver is used extensively in modern medicine, including catheter tips and surgical dressings. At the element level, silver is the most electrically and thermally conductive element on the planet. These properties make metallic silver fatally disruptive to the electrochemical functioning of simple bacteria. Silver ions bond with key enzymes, proteins, and DNA to kill bacteria very quickly. And unlike chlorine-based solutions, where the chlorine gets consumed during disinfection and requires retreatment, silver remains free and active in the disinfection process, moving on from one bacterial cell to the next. So once the silver-based solution is in the water, that water is kept clean and is ready for consumption at any time. So I submit to you as water sector professionals, silver-based solutions can be an extremely effective alternative to chlorine disinfection. Part of my argument here is based on the prevailing theory over the last 50 plus years that says chlorine-based compounds are universally safe and effective, and any health side effects are acceptable risks relative to the health effects of waterborne pathogens. Today, that wisdom is only partly correct. In fact, it may be presumptuous to consider these acceptable risks any longer acceptable in the face of this emergent technology. Earlier, I shared this slide, which had noted a particular study in 2007. A growing body of medical and professionals and institutions has determined that chlorine disinfection byproducts are a leading cause of bladder, stomach, colon, rectal cancers, and have been linked to heart-related diseases. Silver-based disinfection does not produce any trihalmethanes or any other harmful byproducts. SV36 is the generic formulant name of one such silver-based solution that we have developed. Let me take a few minutes to describe this solution and share some test results conducted by independent laboratories that are collaborative centers to the World Health Organization. SV36 is a silver-based stable suspension that has been tested by independent laboratories to be extremely effective in killing a broad spectrum of waterborne bacteria, including E. coli, Salmonella, and cholera. For over 20 years, SV36 has been the exclusive emergency relief water treatment option used by the government of Mexico, replacing chlorine tablets. When there is a natural disaster, flooding, for example, government officials distribute these 30 milliliter bottles in the communities affected. Families find whatever source of water is available, add 1 drop per 2 liters of water in a container, wait 30 minutes, and the water is safe to drink. Once the community has recovered from the natural disaster, then families use SV36 for everyday disinfection of water for point of use consumption, as well as for maintaining safe water in household storage tanks, which are commonly seen on the ground or on the rooftops. Several independent laboratories have validated the effectiveness of SV36 in killing a broad spectrum of waterborne bacteria. The kill rates shown here are based on a 30-minute duration. SV36 can also be applied to clay pots as a means to disinfect water. Using earthenware jars, the laboratory in France demonstrated a log 6 kill rate for all bacteria tested. As part of registering SV36 with the Ghana Food and Drug Board, we had our product tested by the Noguchi Memorial Institute, another World Health Organization collaborative center. In addition to successfully evaluating the effectiveness of SV36 against waterborne bacteria, the laboratory reported high kill rates for other bacteria, including staph, which causes skin infections, bacillus, a foodborne pathogen that occurs when cooked food is left out after a period of time, Klebsiella, which can cause a range of diseases, including pneumonia, candida, a fungus often associated with yeast infections among women, and aspergillus, a common mold found on fruits. And then per our request, the Noguchi Memorial Institute conducted additional testing on a variety of unfiltered water sources collected nearby. These results, in combination with those on the preceding slide, convinced the Ghana Food and Drug Board to approve our product as a water disinfectant. SV36 underwent similar testing in Nigeria and has been approved by NAFDAC. Right now, we are pending approval in Haiti. Earlier, I had presented this slide regarding the input from the United Nations panel on what the term effective truly means. Let me quickly run through each of these requirements as it relates to our silver-based solution. First of all, SV36 is extremely effective in killing waterborne bacteria, and it stays active in the water until all pathogens are gone. SV36 is extremely safe to use. There are no harmful health side effects, even if the water is severely overdosed. SV36 is compact. In Mexico, 130 milliliter bottle can disinfect up to 1,200 liters of water. And if not required to drink that water after 30 minutes of treatment, then one bottle can disinfect even a greater volume. SV36 is simple to use. Add 1 drop per liter of water and wait 30 minutes. The SV36 is portable. A 30 milliliter bottle can be carried anywhere for away from home use. SV36 has no taste or odor. Because the silver is always active, SV36 prevents pathogens from forming inside storage containers. SV36 has a very long shelf life. Its effectiveness does not degrade or expire with time. So one reason why we're excited about this alternative to chlorine-based solutions is how well the benefits of SV36 align with these UN requirements. I will open up for Q&A in a minute, but I'd first like to compare the maintenance required to ensure safe drinking water in long-term storage for 2 solutions: chlorination and treatment with SV36. After 3 days, per Bill's comments, conservatively, the chlorinated water needs to be tested for chlorine residual and redosed if required. No maintenance is required for SV36. After 3 more days, chlorinated water needs to be tested again and redosed if required. No maintenance is required for SV36. This same maintenance schedule goes on after day 9, day 12, and day 120. As a consequence of periodic chlorinated treatment, there is a possibility of recontamination leading to the production of disinfection byproducts from the presence of bacteria, biofilm, or algae. In addition, over time, chlorine can degrade the integrity of storage tanks, pipes, and valves. None of these issues will occur with a silver-based solution. I have a proposition for this group in a minute, but first I'll take questions regarding SV36 or any other topic that we have discussed today. Bill, have there been any items in the chat box or questions regarding disinfection in the survey that we did last week?
Yes, there is a question from Ezekiel Francis regarding the residual when using the silver-based disinfection. I've answered that briefly on in the chat utility, but it's important to understand that it is the presence of and not the chemical bonding with silver that results in disinfection. It is simply the presence of the silver that kills. And so silver disinfection does not include or does not require anything for residual. The silver itself remains in solution and is the residual. I can tell you anecdotally that we have applications where the product was dosed as David instructed, as 1 drop per 2 liters, and it stayed clean for 2 years in a sealed black high-density polyethylene storage vessel. And so we're absolutely certain we can get 2 years out of properly dosed water that is stored in a sealed container.
Fantastic. Any other questions from the chat box?
The other question in the chat box, again from Ezekiel, is whether or not we need filtration. And certainly between total dissolved solids, anything that requires flocculation or any kind of filtration, your water should not be cloudy. It should not have high turbidity. That turbidity hides microorganisms, and it hides pathogens that will eventually get out and contaminate the water. And so what we do, or what we will say with SV36, is if the water comes out of the hole clean and requires very simple filtration, whether that's sand filtration or membrane filtration, whatever it happens to be, it can stay clean with the use of SV36.
Yeah, I will say the community water points that were done for the United Nations project in Mexico, that was a straightforward filtration system as it went from the borehole to the Olger unit and then into the storage tank. Was it sand filters, or were those membrane filters that were used, or a combination of both depending on the location?
The ones that I saw, David, were sand filters. There may have been other filtration in use, but the ones I saw were very simple sand filters.
Okay. As I was talking, I saw another something else happen in the chat box. Are those questions to answer?
Yeah. Are there other municipalities in the hemisphere using SV36? I know that because of its status at CAWASA, which for us in the United States is kind of like the Food and Drug Association, the FDA, or the Food and Drug Board, as you'd see in some countries. It is approved for use in Central America. I am not aware of any other municipalities that are using it. It is used institutionally for disaster relief because of its ease of use for away from home and compromised solutions. The SV36 is often used instead of the boil water caution because it has essentially the same effect.
Okay. The use of it after disaster relief, because it is a great remedy to treat the waterborne pathogens that occur often in flooding, such as E. coli, salmonella, and cholera. But then once the communities have recovered from that, then the community uses the SV36 just for everyday consumption, and they use it in their point of use containers for immediate use or for long-term storage. So that's where SV36 has been used in particularly in Mexico, where we manufacture. So what I'm going to do is I've got time for questions at the end of this, but let me get to my last slide here for today. And my last slide for this webinar is really an invitation to each of you here today. My email address is here. If you and your team are interested in using our Ogre technology or SV36 product for a trial to initially clean water or keep water safe in long-term storage, then we will offer free use of either solution to you. With a subject heading of CAWASA trial, simply email me by the end of this week with your interest, and I will send you a brief form to complete as a request from your trial. And I would like to propose, per Ignatius's approval, that findings from your trial be presented to CAWASA members at a future webinar. So with that, I thank you for your attention today, and I open our discussion to any other questions one last time. And Bill, I did see some additional comments in the chat box.
Yes, David, I'm answering those as you speak.
Okay. Okay. If there's any questions about the use of our two solutions for a trial, please include that into the chat box as well.
Yeah, David, if there's no other questions, I guess I can answer these live. Mr. Timothy asked, what are the cost benefits as compared to chlorination? When you look at the user level, not necessarily at the municipal level, but at the user level, our experience in Africa is that we're cost competitive with the chlorine products. We're easier to handle. We have higher concentration, so it takes up less space, creates less packaging and waste in its use. And we have been, and we believe we are, and will remain cost competitive. Your companion question was relative to treated wastewater. We've not used it on wastewater. That's a whole different kettle of fish when it comes to treatment, as opposed to disinfection of drinking water. And I'm not aware, and I've been involved with this technology for 15 years. I'm not aware that we've ever worked on the wastewater side. Sabiji has asked, what are the long-term effects of SV36 with consumption? Because the silver is ingested, that is a legitimate question. We've got guidance from the US EPA regarding ingestion and the body processes and waste processes related to silver. The long-term effects, let me see if I can put this subtly. If you were to consume 4 liters a day for 125 years without using the toilet, you would reach the nuisance level identified by the US EPA. The amount, because of the size and the particle size that we use, we get very, very excellent disinfection with extremely small amounts. You are looking at, in that 30 milliliter bottle that is a year's worth of drinking water, you're looking at less than 1/10 of a gram of silver in there, and the body processes that very efficiently. Next question, Mr. Terry, or could be Miss Terry, I'm sorry. Is SV36 affected by temperature and pH of the water? pH affects every disinfection technology. We are much less affected by that. The pH of the SV36 product is 7.0. Now, that's logical because it is pharmaceutical grade water, 99.64%. It is affected, but not to the degree that you would see with chlorine. And the final question in the chat box is, we mentioned NaCl in the solution and the impact on consumption, particularly for consumers with predisposition to hypertension. The NaCl does not interface with the water supply in any way, shape, or form. And so as a result of that, there is no opportunity for the sodium chloride, the salt, to get into the water supply. It is the gases only. And again, as David described, these are physically violent gases with extremely short half-lives, and they literally tear apart viruses, bacteria, and protozoa that stream past them. They only last a very short time. And as David said, because of the ability to concentrate and kill those in the Venturi injector, we require only a very small, we use less than 1 part per million of chlorine in order to maintain the cleanliness of the water that comes through on the other end.
Great. I don't see any other questions coming into the chat box. So if you do have other questions, you certainly have my email address there to feel free to forward those to me. And if you're interested in conducting a trial, please let me know. And with that, I'm going to thank Ignatius for his gracious ability to host this for us and turn it over to him right now.
Right. Thank you again, David, and your colleague for leading us through this webinar. And I think it is an interesting perspective. I think we had quite a few participants, well, pretty engaging in the chat room, and the responses were good. So again, I'd like on behalf of CAWASA to welcome all the participants to the first of our webinars for 2023. And again, to thank Valerie Jenkinson of Operators Without Borders for making that connection on our behalf. And we really appreciate the time you place in this and engaging the operators prior to the webinar through the survey. I think that was an interesting survey. And of course, we are going to post this on our recording on our YouTube site so that those who missed it would be able to locate it. And of course, I think it would stir some more discussion. We have an active chat room outside of this platform. So I'm sure it will be able to stir some other thought-provoking conversations as we progress. So again, many thanks to you, David. And I didn't remember your partner's name.
Bill Dilge is my partner that joined us on the call today.
Okay. Thank you, Bill. And
It's certainly been my pleasure. If I could offer you one parting message.
Thank you.
It's that there are some very smart, creative people working on ways to help with water treatment. And I would encourage you to keep your minds open and participate in some of these trials. I think you will find the technologies very simple, very easy to use, and a significant improvement over what's been done for the last 50 years.
Yeah, interesting. In fact, I remember once participating in a water expo. I think that was in Florida, in Miami, and there were some presentations for alternative treatment, particularly using silver and I think copper for treating water where people are sensitive, particularly in pools where people are sensitive to chlorine in swimming pools. So that's another perspective that you have introduced to us, and we're sure we'll be sharing that with our other colleagues. Thank you very much.
Great. All right. Ignatius, thank you for your time, and thank you all who joined us in our presentation this afternoon.
Okay, everyone, thank you. And this brings us to the end of our CAWASA Wednesday webinar. And if it's Wednesday, it's the discussion on all things water and wastewater. Bye for now. Have a good evening.